A very good day to the professors that are here today. My name is Lim Siyong, and I'm currently in the first semester of my final year, which leads me to talk about the progress of my thesis, entitled Vision Transformer Optimization using Two-Phase Switching Optimization Strategy. This presentation will be divided into 5 sections. Firstly, I will introduce the topic of this paper and give a little context. After that, I will dive into the objectives behind my research. Once that is clear, I will explain how my research was carried out. From there, I will present the current results and the analysis of my findings. Lastly, I will conclude the presentation and discuss the work I will carry on in FYP2. First, let me introduce to you the topic of my paper. Deep learning neural networks are an essential and popular tool recently to handle various tasks such as image classification, speech recognition, natural language processing, and computer vision tasks. A diagram of the basic neural network is shown here. However, let us focus only on backpropagation. A neural network learns by passing the derivation of errors in a backpropagation manner. This is where optimization methods come in. There are generally two types of optimization methods, first order and second order derivative. First order methods use the first order derivative with respect to each weight. However, these can pose various issues, which we will see later. Second order methods were introduced to improve the performance in a single optimization step by using the additional curvature information to support the learning efficiency in the object functions optimization. We can start formulating the objectives based on the problem statement. The first objective is to use a first-order optimization algorithm, in this case ADAM, on the Vision Transformer application using the CIFAR-10 dataset, which I will explain in the next section. After that, I will switch to SDAGD and perform the same task and use the results to make a comparison. After better understanding the current state of these algorithms, I will modify the Hesian-free SDAGD optimization algorithm to improve its performance. Now, let me show you the details of how I've carried out my research. Previously in the objectives, I mentioned that I would use the CIFAR-10 dataset. Here, let me explain what it is. It is a dataset comprising of 60,000 color images that are 32 by 32 pixels in size. There are 10 classes in this dataset which are written here. You can also see some of the example images shown here. Using this dataset, we will apply it to the Vision Transformer model. In short, a vision transformer employs a transformer architecture and targets vision processing tasks such as image recognition. The vision transformer computes relationships among pixels in various small image sections, and each section is arranged into a linear sequence and multiplied by the embedding matrix. With the positional embedding, the result is fed to the transformer encoder, and the class with the highest probability is predicted. As I've said earlier, I will use the ADAM optimizer during my training. Here is the weight update equation of this optimizer. ADAM is used to accelerate the gradient descent algorithm by considering the exponentially weighted average of the gradients. Therefore, this optimizer's two critical parameters I highlighted here. The first term is the average first moment, whilst the second term is the second moment of the gradient, as highlighted in orange. Here is a brief overview of the parameters I've set when training my vision transformer model. Most of the parameters here were set accordingly to the benchmarks set by other researchers. The only variable in my experiment focused on is the learning rate, which I will vary to better understand the optimizer at hand. Another important thing to note is that I trained the model for 30 epochs. After performing the experiments, I obtained the results and hence performed my analysis on the results. Here, we can see that when I use a learning rate of 0.01, I only obtained a testing accuracy of 0.2058 and a loss of 2.1310. However, when I set the learning rate to 0.001, the results instantly increased by a significant margin, rising to an accuracy of 0.6744 and a loss of 0.9128. The learning curves can be diagnosed in terms of underfitting and overfitting. From the learning curves of the training loss, the model is a flat line with noisy values and a relatively high loss when the learning rate is set at 0.01. From these indications, we can deduce that the current model is underfitting as the model cannot learn the training dataset. Not only that, we observe that the learning curve of the training loss when the learning rate is set at 0.001, as shown in orange over here, decreases and continues to decrease at the end of the plot. This indicates that the model can still learn more with potential improvements. Ideally, we would want the graph to decrease to a point of stability, otherwise known as a good fit. The learning curve for the training and validation loss when the learning rate is set as 0.01 shows improvement but with a large gap between both curves. This means that the training dataset does not provide sufficient information to learn the problem relative to the validation dataset used to evaluate it. One possible reason is a lack of adequate examples in the training dataset. On the other hand, significant improvement and a small gap between both curves can be seen when the learning rate is set as 0.001. This means that the training and validation dataset is relatively representative. Up to now, I have already implemented the Vision Transformer using Adam and found its problems. After that, in FYP2, I will switch to SDAGD and determine whether the performance is better if a second-order derivative is used. Once I get a better understanding of optimizers, I will begin to modify the Heijin-free SDAGD optimizer and test it on the Vision Transformer like the previous tasks. My presentation has come to an end. Thank you again, and I hope that this presentation has given you a much clearer understanding of the second-order derivative optimization methods in deep learning neural network. Thank you.